All right, here we are. This is the video for pages 43 through 59. First question, we have a limit as x goes to infinity of this whole thing. Um, it might be a little easier to see what happens here if we multiply this out. So we would get 6x minus 2x squared minus 3 plus x over the bottom one. I'm going to do it in my head. X squared plus 2x minus 3. So if you notice, the highest degree term in the numerator is negative 2x squared. The highest degree term in the denominator is x squared. We can take the ratio of the highest degree term, since the degrees are equal, to take the limit as x approaches infinity. So this becomes negative 2 over 1, or just negative 2. There is a problem similar to this in the previous video. If you look, you can talk about just how to do this a little more analytically by dividing by the highest power in the denominator. Number 2, we have f of x is that. Then we want to find f prime of x. So overall, we have a product rule problem. We have this times x squared plus 2 to the third. Derivative of x plus minus 1 is 1. Derivative of x squared plus 2 to the third is 3 times x squared plus 2 squared times the derivative of the inner piece, which is 2x. So now, to form the derivative, we get f prime of x is equal to x squared plus 2 cubed plus 6x times x squared plus 2 squared times x minus 1. That is not the answer. So what they want us to do here is actually factor. They want us to factor out an x squared plus 2 squared. That is the GCF. So if we do that, we'll get x squared plus 2 squared outside. Inside we'll have x squared plus 2 to the first plus 6x times x minus 1. Okay, so now we can simplify that second factor. Okay, if we distribute, we would get 6x squared minus x. X squared plus 6x squared is 7x squared. Minus x plus 2 ends up being that second factor. And that answer is choice nobody, because it's minus 6x, which makes this minus 6x there. Choice D is the answer. All right, number 5. The limit as x approaches 0 is different than the limit as x approaches infinity. Anytime you have a number, you try plugging it in first. And as you see, the top and the bottom will become both 0. 0 over 0 is a hint to do some algebra. The algebra we can do here is factor out the GCF. So in the top, we get a GCF of x squared, which would be 5, leaving us with 5x squared plus 8. The bottom, the GCF, is x squared as well, leaving us with 3x squared minus 16. This is the limit as x goes to 0. These go away. We get the limit as x goes to 0 now of 5x squared plus 8 over 3x squared minus 16. Now if we plug in 0, these terms vanish. We get 8 over negative 16, which is negative 1 over 2, choice A. Number 6, we have this function defined above. Which of the following statements of f are true? So notice f of x is, if we do x minus 2 times x plus 2 over x minus 2, if x is not equal to 2, and 1 if x is 2. So we can cross these out. So this function is really, f of x is just x plus 2 if x is not equal to 2, and is 1 if x is 2. So we can quickly sketch this, and if you sketch this pretty quickly, it will give you a very nice pictorial way to do this problem. The graph is x plus 2 if x is not equal to 2, so it's just the line with slope 1 and y-intercept of 2, as long as x is not 2. So we would put a hole there at 2, and we know the function value at 2 is actually 1. So here is our graph. And so does the limit exist? Well, this is the shutter method. I don't care about what's happening on the inside at 2. I care about what's happening from both sides here. We are approaching 4, so the limit exists. So that's actually true. Sorry, true. The function is not continuous because we have a hole. And automatically, if a function is not continuous, we are not differentiable there, so 1 only is the answer. Number 7 says a particle moves along the x-axis with a velocity given by that function for time t is greater than or equal to 0. If the particle is at position x equals 2 at time t equals 0, what is the position of the particle when time is 1? So we have the velocity is, 3t squared plus 6t. If we want to go backwards to position, we take the antiderivative, which is we add 1 to the power divided by the power plus add 1 to the power divided by the new power plus c. Simplifying, we get t cubed plus 3t squared plus c to be our position function. Now we don't know what the position, we don't know what c is, but at time t equals 0, so time t equals 0, the position is 2, so 2 is equal to 0 cubed plus 3 times 0 squared plus c, making c equal to 2, otherwise known as the initial position. So now we have x of t to be t cubed plus 3t squared plus 2. Once we have that, the position of the particle at time t equals 1, x of 1 is 1 cubed plus 3 times 1 squared plus 2. 1 plus 3 plus 2 is 6. There's our position. 6 is the answer. Choice B. Number 8. If f of x is cos of 3x and f prime of pi over 9 is, we need a chain rule here because we have cos of stuff. Derivative of cos of stuff is negative sine of stuff times the derivative of the stuff, which is 3. So we have f prime of x is negative 3 sine 3x. We want the derivative at pi over 9. So this is negative 3 sine of 3 times pi over 9, which is pi over 3. We need to achieve the sine of pi over 3. Looking at our reference table, a reference triangle, pi over 3 is 60 degrees. So we will draw a 60, 30, 90 right triangle, labeling appropriately. Sine of pi over 3 is the opposite over the hypotenuse. There's our sine value, so we would get negative 3 times radical 3 over 2, which is just simply negative 3 root 3 over 2. And that is choice E. Number 11, the graph of f is shown above. Which of the following could be the graph of the derivative? We've done these at the beginning of the year, and you can probably reason this out plenty of ways. Here are your 0 slopes. So you have 2 zeros, not 3, not 1 at the origin. D right now is a candidate, and E has no 0. So just by that, you eliminate 3 choices. And now, if you think about it, the function is increasing till you get to this first guy. So your slopes are positive. Slopes are positive on B, but negative at D. So B is your answer. Next question. If f of x is 2x squared plus 2x, then the derivative of f of ln of x is equal to. Well, let's talk about something for a moment. We want the derivative of f of ln of x. Well, what is f of ln of x? F of ln of x is, instead of having an x wherever we see, wherever we see an x, we're going to put in ln of x. So we really want the derivative of this. We want the derivative of ln of x squared plus 2 ln of x. So now we want the derivative of ln of x squared. We have the derivative of stuff squared. The derivative of stuff squared is 2 times the stuff times the derivative of stuff. The derivative of ln of x is 1 over x, plus the derivative of 2 ln of x is 2 times 1 over x. So this becomes 2 ln of x over x plus 2 over x, which has a common denominator, so we can pretty easily add these fractions up. Choice A. Number 14, this is a tricky question if I remember correctly. The polynomial function f has selected values of its second derivative f double prime given in the table below. Which of the following statements must be true? All we know is that these are 4 values of the second derivative. We know nothing else about the second derivative. But we do know we have a polynomial function, okay? Which means all the derivatives are continuous. In fact, not only that, all the derivatives are differentiable. That's all we know, but we only know these four values. All right. So first of all, f is increasing on the interval 0 to 2. Well, this tells f double prime tells us strictly about concavity of f. So f being increasing or decreasing is just gone. F has a local max at x equals 1. Well, let's analyze that for a moment. The second derivative is 0. Okay, so what that means is you could have a possible inflection point if the second derivative at 1 is 0. But that does not mean that you get a max. It could just mean you have an inflection point, so we don't know that that's true either. D, the graph of f has a point of inflection at x equals 1. Well, we don't necessarily know that either, because, for example, let's say at f double prime, okay, we had at 1 we have a 0, but maybe before we get to 1 our second derivative is positive, and maybe after we leave 1 it's positive, and then somewhere in the middle, because we know that the second derivative of -2 is -7, maybe somewhere in the middle here the sign changes. We don't know that the sign changes at 1 of the second derivative, so we do not know for sure that the graph of f has a point of inflection. What we do know, however, is the graph of f changes concavity on the interval 0 to 2, and here's why. If you were to plot these points on a graph, 0, 5 is on the graph, 1, 0 is on the graph, 2, -7 is on the graph, and whatever, we don't care about 3, 4, believe it or not, at this point. Now, what I was saying before is, we could have done a touch and go at 1. So maybe 1 is not an inflection point because the second derivative did not change its sign. But what has to happen is because we're dealing with a polynomial function, its derivatives are differentiable. So what happens is, namely, that the derivative is continuous. Second derivative is continuous. So I eventually have to cross the x-axis by essentially the intermediate value theorem. Says I have to cross the x-axis somewhere, specifically between 1 and 2. So there is a place where the graph will change concavity on the interval 0 to 2, since 1, 2 is a subinterval. So choice E. That is a tricky question, I think quite well written to get to see if you really understand the concepts. 16 of x, sine of xy equals x, then dy dx is equal to. So we have sine of xy equals x, taking the derivative on both sides here. Derivative sine of stuff is cosine of stuff times the derivative of the stuff, which is the product rule. We'll do that in a second. Derivative of x is 1. So x, y, derivative of x is 1, and we have dy over dx. So we have x dy over dx plus y. So we have cos of xy times all that stuff is equal to 1. Now we want to get dy over dx. So easy way to get, first of all, let's get rid of cosine of xy by dividing. I don't want to distribute this through. I mean, that would make a bigger mess. The idea is to get dy dx by itself. So we have x dy over dx plus y equals, my initial instinct is to convert 1 over cos to secant. But if you notice, the choices don't involve secant. So I'm actually going to leave 1 over cos xy just as it is. So we'll shove the y over. See. So we get x dy over dx is equal to 1 over cos xy minus y. And we have to divide by x. Dividing by x, if we look at the choices, we have to be a little careful here. We're dividing by x. We could divide each fraction by x, which would make this happen. Remember, the x has to go in the denominator. So dy over dx is 1 over x cos xy minus y over x. That is not a choice. So what we can do is combine this to make this one fraction. Multiply this guy up here by cos xy. We'll do the trick. That'll get a common denominator. So we end up with dy over dx equaling 1 minus y cos xy over x cos xy, which hopefully is a choice. And it is choice D. Yay. All right. So number 18 says, in the xy plane, the line x plus y equals k, where k is a constant, is tangent to the graph of y equals x squared plus 3x plus 1, what is the value of k? Interesting. So we know x plus y equals k is tangent to the graph somewhere. Well, this is the line y equals negative x plus k, which has a slope of negative 1. So we want to find out where y equals x squared plus 3x plus 1, where does it have a slope of negative 1? That would be helpful because that would make sure that this line here is tangent to this curve. So let's take the derivative. Y prime is 2x plus 3, and we want to find out where the slope is negative 1. So we get 2x is negative 4, x is negative 2. Well, if x is negative 2, we can figure out the y value of that curve. So if x is negative 2, well, y would be negative 2 squared plus 3 times negative 2 plus 1, which is 4 minus 6 plus 1, which is negative 1. So now we know the point. Negative 2, negative 1 is precisely where the slope of the tangent line is negative 1. Well, that will help us actually find this constant here. We can take x and y and plug them in, and we will be able to find the constant. So y is negative 1 equals negative times negative 2 plus k. We get negative 1 is 2 plus k. Subtract 2 from both sides, and k is negative 3. So the value of k is negative 3. Love that problem. That is a good one to think about. That is a definite candidate, something like that along the lines on the midterm. Number 19, what are all the horizontal asymptotes of the graph of y equals 5 plus 2 to the x over 1 minus 2 to the x in the xy plane? This is a problem that was actually not counted on the AP exam because so many kids got it wrong. And we did a lot of these at the beginning of the year. Probably too many, but if we want to find horizontal asymptotes, we have to consider both directions, both the direction of x going to positive infinity and the direction of x going to negative infinity, because they could lead us in two different directions. You could have two different horizontal asymptotes of a function. And so we have to really consider two limits. We have to consider the limit as x goes to infinity, and we have to consider the limit as x goes to negative infinity. Well, the limit as x goes to infinity, 2 to the x is getting huge. So what I like to do is divide all the terms by the thing that's getting huge in the denominator, which is 2 to the x. We get 5 over 2 to the x plus 2 to the x over 2 to the x over 1 over 2 to the x minus 2 to the x over 2 to the x. So if we take a look at what happens here, these 2 to the x's over 2 to the x become 1s. And these other guys go to 0. So we end up with 1 over negative 1, which is negative 1. That is one of our horizontal asymptotes, in fact, the one that's going to the right. Now we get to this guy. Limit as x approaches negative infinity. If you think about what y equals 2 to the x looks like as a graph, 2 to the x gets very tiny, close to 0. So the limit as x approaches negative infinity of say 2 to the x is 0 as x goes to negative infinity. So these are not getting big. They are actually getting small towards 0. And so we get 5 over 1, which is 5. So we get y equals 5 as the other horizontal asymptote. People miss this one guaranteed. So y equals negative 1 and y equals positive 5 are both horizontal asymptotes. Choice E. Number 20, let f be the function with a second derivative of that. Where are the x coordinates at the points of inflection? This is a very basic question. Make a number line. F double prime. Our roots are 0. Well, I'll put 0 on the left. Hold on. 0, 3, and 6. So our derivative here is x squared, x minus 3. That looks like a plus. That's not going to work. X minus 3 times x minus 6. So x squared is always positive. If we're to the left of 0, say negative 1, x minus 3 is negative, x minus 6 is negative. Positive times a negative is a positive. Then picking a number between 0 and 3, say 1. X squared is positive. 1 minus 3 is still negative. 1 minus 6 is still negative. So we did not make a sign change there. That was a fake out. Between 3 and 6, we're plugging in 4. 4 minus 3 is 1, which is positive. 4 minus 6 is negative. So positive times a negative is a negative. And past 6, 7 minus 3 is positive. 7 minus 6 is positive. We're all positive now. So how many points of inflection do we have? Points of inflection are where the sign changes. So at 3 and 6 only are our points of inflection. All right, 21. A particle moves along a straight line. The graph of the particle's position at time t is shown above for 0 to 6. The graph has horizontal tangents at t and 1 t equals 5 and point of inflection at t equals 2. For what value is the velocity increasing? Well, velocity increasing, okay, if we're looking for where v of t is increasing, or in general, if we're looking at when a function is increasing, we look to its derivative, whether it's positive or negative. So if we're looking at v of t, if we want to find out where v of t is increasing, we're looking to where its derivative is positive. Now the derivative of velocity is acceleration. So we want to find out where the acceleration is positive. So what I suggest you do, this is a position graph. We need to make 2 number lines based on this. So I'm actually going to shove this information to the side or up here. This is what we want to do. Okay. I'm going to make 2 number lines. One is going to be for velocity. Okay. And then we can make, actually, in reality, we can really just make one for acceleration. Okay. We can really just make one for acceleration and skip the velocity number line. Now, as you notice, in terms of derivatives, we have x of t, then v of t, then a of t. So we're really looking at the second derivative. We thought of this as f double prime, f prime, f double prime. So we're looking to fill in the acceleration number line, which asks us to really look at where x of t is concave up or down. So we are concave up until we get to the inflection point at t equals 2. Then we are concave down after that. So if we're concave up, concave down, there's our number line. Now a of t, we want it to be positive because that's where the velocity is increasing, 0 to 2. A little more conceptually, on the interval 0 to 2, velocity are the slopes along the graph of x, along the graph of position. On 0 to 2, those slopes are increasing. Those slopes are going from being more to negative to positive. And that's exactly why you're accelerating in the positive direction, because in order for my velocity to become more positive, someone has to be pushing me in that positive direction. All right, 24, we have a function which is twice differentiable. That just means that f prime and f double prime exist everywhere. Okay, f of 2 is 1, f prime of 2 is 4, f double prime of 2 is 3. What is the approximation of f of 1.9 using the line tangent to the graph of f at x equals 2? Well, first we would need to actually achieve what that line is. Here's the equation of the tangent line. At x equals 2, well, we know a few things. X is 2, obviously. We know y. Y is the y value here, which is 1. And the slope is the derivative, which is 4. So there's our tangent line. And now we want to find out what the approximation of f of 1.9, or the y value at 1.9 is when x is 2. So what we're going to do is we're going to use this point now. We're going to let x be 1.9. Whoops, 1.9 in here. And we're going to find out the y value. So y minus 1 is 4 times 1.9 minus 2. Y minus 1 equals 4 times 0.1, or negative 0.1 rather. So y minus 1 is negative 0.4. Add 1 over, y would be negative 3, long day. Y would be 0.6. That would be our approximation, choice B. 25 says let f be the function defined above where c and d are constants. If f is differentiable at 2, what is the value of c plus d? Interesting question. If f is differentiable, this really means 2 things. 1, differentiable. You might be saying, well, duh, Mr. B. But 2, it means that the function's continuous. So if the function's continuous, what that means is at x equals 2, both the pieces equal each other. So c times 2 plus d is equal to 2 squared minus c times 2. This simplifies to 2c plus d equaling 4 minus 2c. The other thing that's true, this is based on continuity. The other thing that's true is that the derivatives are equal. So the derivative of cx plus d is c. The derivative of x squared minus cx is 2x minus c. But at x equals 2, this would be c equals 4 minus c. Well, if c is 4 minus c, we can solve for c. So add c to both sides. 2c is 4, c is 2. And if c is 2, we want to find d, because they asked us for c plus d. That's their way of saying get c and get d and add them up. So 2 times 2 plus d, that has to equal 4 minus 2 times 2. Well, 2 times 2 is 4, plus d is 4 minus 4 is 0, so d is negative 4. So d being negative 4, c being 2, negative 4 plus 2 is negative 2, choice B. 26, what is the slope of the line tangent to the curve of y equals arctan 4x at the point which x is equal to a 1/4? A little review here. The derivative of arc sine of x is 1 over square root of 1 minus x squared. Yes, you have to know this. The derivative of arc tan x is 1 over 1 plus x squared. That's what we'll use here. So the derivative of arc tan of stuff is 1 over 1 plus the stuff squared. So the stuff is 4x times the derivative of stuff, which is 4. So our derivative, f prime of x, is 4 over 1 plus, if you wanted to simplify 4x quantity squared, it would be 16x squared. Now, we want to find out this value at 1/4. So f prime of a fourth is 4 over 1 plus 16 times 1 over 4 squared. 1 over 4 squared is 1 over 16 times 16 is 1. So we get 4 over 1 plus 1, which is 4 over 2, which is 2. And 2 is the answer. Choice A. And last but not least, 28. Let f be a differentiable function, and they give us some values. The function g is differentiable, and g is the inverse for all x. What is the value of g prime at 3? So I like to set up my little table for this. My little invented table here. So we want g prime at 3. So think about that. What that means is my point on g is 3 comma somebody, which means the point on f is somebody comma 3. So we're really looking for f's y value to be 3, which corresponds to f of 6 being 3. We have f prime of 6 available to us. That's negative 2. So g prime of 3 is the reciprocal of that, which is negative 1 over 2. Choice A. And that's it.